Okay, the introduction's out of the way. I'll try and make this as friendly as possible, but there are a few things that will undoubtedly seem foreign to you, but that's the way it is. So feel free to interrupt me or raise your hand or whatever. All right, I like to start out with the conclusion first, and then kind of gives you an idea of where we're going. And if this thing breaks, then we can all go home. Anyway, the things that you kind of want to, when you're thinking about this, if you're talking to people, the public and so forth, is that Lake Tahoe started forming about 3.5 million years ago. It lies in what we call a structural basin, geologically speaking. I won't really get too much into what that really means, but it's defined by active faults. We'll talk about what faults are. Okay, here are these big words. Pliocene, Quaternary age. This just means the last few million years of Earth history. Volcanism played a role in forming the lake. Throughout its particularly more recent history, during the Pleistocene, which is basically the last couple millions of years, Tahoe was repeatedly dammed by glaciers. It caused the lake levels to rise. There'd be outbursts, and the lake would drain. But anyway, the lake level, we have evidence for lake levels well above the modern level that we see today. We'll talk a little bit about very little bit. When I say we'll talk a little bit about some of this stuff, I really mean it. But we'll look at some of the evidence. Large debris slides have occurred on the west side of the lake, and even much smaller ones to a certain extent on the north side, as well as elsewhere in the basin. They occurred likely in response to seismic shaking, earthquakes.
Question.
Yeah.
How far south did the lava platform extend from the volcanic activity?
Probably just, basically the North Shore. There are bits and pieces of volcanics around here, but the main ones were, at this end.
So it's my understanding that the shelf near Tahoe City was caused one of the underwater landslides. Was that volcanic in origin?
The landslide or the rocks?
The debris that slew.
I don't really know whether that's volcanic. It would make sense that they're probably volcanic rocks that were involved in the the big slide or whatever, as opposed to what's going on the west shore. Didn't answer your question, did I?
Maybe get to where there's some maps.
Yeah, that'll help a little bit. And then, since we're in the realm of climate change, there is evidence that there have been severe drought throughout the western United States, which impacted the Lake Tahoe region and caused a tremendous decline in lake level well below the natural rim. Okay, so we'll talk a little bit about physiographic setting, the geology and tectonics, the faults and evidence for them, the McKinney Bay landslide complex, the ice ages, Tahoe lake levels, and implications for changing lake levels. So one of the cool things about this particular area is that there is a great diversity in the geology and the geomorphology in the Lake Tahoe region. We have a variety of things in terms of plate tectonic influence, volcanism, glaciers, and using modern techniques to look at things. So it's a great place to be. Before we get too far into this, a couple of definitions. Geology, it's just the science. We talk about the study of the earth, not so much the water, but the solid earth, the rocks that the earth's composed of, and all the processes by which they form, as well as overall the history of the earth. Geomorphology, I will talk about this. It's the study of landforms, in the most general sense. It's really the study of the processes that create and modify landforms, and it also encompasses the evolution of the landscape. Plate tectonics is a scientific theory describing large-scale motion of the Earth's lithosphere, the hard outer shell of the Earth. It's comprised of the crust and upper mantle. You've probably heard a lot of these terms just reading magazines and newspapers and so forth. Fault, that'll be a term that comes up time and time again. It is a planar fracture or discontinuity within a large mass of rock. And across that planar discontinuity, there has been relative movement from one side of the planar feature to the other side. Oops. And it's a rapid release of energy when you have movement along this plane that releases a tremendous amount of energy. And that's what causes the ground to shake and earthquakes to occur. Fault zone, just because these things aren't just a simple line that you can sometimes they are, you put your hand on it. Generally, a fault is not just a simple plane, it's a very complex zone of anastomosing planes of discontinuity and so forth, so don't be thrown by the word fault zone. Okay, let's get located where we are physiographically. Here's North America, and we are over here. This is the Great Basin, physiographic province. We're surrounded by the Colorado Plateau to the east, and the Southern Rocky Mountains aren't too far here. A couple other notable points: the Northern Rocky Mountains, the Columbia Snake River Plateaus to the north, and the Pacific Mountain System and the Pacific Coast along the west. Lake Tahoe sits right at the boundary between the Great Basin and the Pacific Mountain System. So it's a unique setting, and just because of where we are within the range and the way the weather systems hit us and so forth, we have up here characteristics similar to the Great Basin, yet somewhat similar to the western part as well. Okay, I have to talk about this just because this puts us into context of why Lake Tahoe is really here, and this is sort of the crux of it. You probably won't have people asking you, well, what's plate tectonic setting here? What's going on here? Well, this is sort of tell you that yeah, it's important, and you can actually say something about it. As I mentioned earlier, plate tectonics is the theory having to do with the rigid outer crust, the outer shell of the Earth. That rigid shell is really is made up of a number of large as well as quite small, but we're going to worry about the great big ones. Plates, individual pieces of the Earth's crust. And they're going to either be very dense, composed of a rock that has very high density. It's a volcanic rock called basalt. It underlies most of the ocean basins. It is so dense that it's able to depress the upper mantle, and that's why we have ocean basins. It's so dense. The continents are made up of something that's more akin to what you see around here, a very coarse-grained, light-colored igneous rock, granodiorite. It has a density that's about half as much as the basalt, so it's going to float higher. So by and large, that's what our continents are made of. The ocean basins are the dense basalts. The interior heat of the Earth drives the relative plate motion. These things are kind of bouncing around. It's the whole circulation of heat within the Earth that actually drives the upper mantle and the lithosphere to actually move, and it moves relative to each other. And where these things come together, we call those plate boundaries. And there are basically three types. There's the transform or strike slip, and that's where if you have, each of my hand is a plate, they slide past one another like this. Think of the San Andreas Fault. That is not technically a plate boundary, but it's close enough. Everybody calls it the boundary between the Pacific and the North American plate, but it's a little more complicated than that. But for all practical purposes, it works. Where they come together, two things can happen. One plate can go under the other plate like this. We call that subduction. And it's usually a denser material like in the ocean floor basalts that are very dense. They will go under the continents. That's subduction. And what happens right above this zone of subduction is you have volcanism. There's extreme heat that occurs as this subducting slab goes deeper into the earth and it begins to melt, and it rises and makes its way to the surface. Or you can have two plates come together in a gigantic collision. So think of India crashing into Asia and the huge high mountains there. That is the result of this collisional convergent boundary. Because there are two continents running into each other, it's two relatively low density rock types that just keeps pushing it higher and higher and higher. The United States, North America, has been through a number of convergent collisions throughout its geologic history. We're not going to worry too much about that. But it was one of the things that helped us understand that between Africa and North America and South America, if you just look at a map, it looks like they can all fit together real nicely. That's because at one time they were all joined together. The other type of a plate boundary is what we call a divergent plate boundary, and that's where the plates are actually moving away from each other. And again, that's driven by material in the deep interior of the Earth circulating upwards, and it basically just pushes the plates to the side, or the plates flow across the top of it. We call that a convergent boundary. Most famous one that we know of is the Mid-Atlantic Ridge, and there's also several out in the Pacific plate. So it just happens to be that where Tahoe is located, right about here, the Pacific and North American plate margin. It's been very complicated throughout its history, so makes for a very complex geologic story here. We're somewhat isolated from the real complexity because we're just sitting in this big, mostly granitic terrain. But the boundary itself is it's been beat up pretty bad throughout the history. Okay, real quickly, I've talked about this because we see some of these rocks here at Lake Tahoe. Paleozoic. Early life, that's basically what that Paleozoic stands for. This is basically what the North America looked like, this white part, 250 to 600 million years ago. It was surrounded by oceans, and there were shallow seas, and within those shallow seas, sediments were deposited, and in our case, a lot of limestone sedimentary rock. We're not going to worry about this too much, but because we do find some of these rocks in the Lake Tahoe Basin surrounding the basin, we've got to mention these. So sometime in the past 80 to 100 million years, the Tahoe region was sitting above. The Tahoe region didn't exist then, but where we are would have been sitting above a subduction zone where a dense basalt from an ocean floor was subducting underneath the continent in the North America. So here we have intense heating at depth. We're looking at a couple hundred kilometers depth, and as you go deeper into the earth, it gets hotter and hotter. So there's melting of both the of this subducting slab as well as what's sitting above it. And so part of this is we're melting continental crust, we're mixing things together. The result is we have volcanism, and we also have the emplacement of the less dense granitic rocks. In the case of the Tahoe region, it's granite diorite is the dominant rock type. Here it's referred to as this gigantic body of igneous rock is referred to as the Sierra Nevada batholith. Batholith is just another word for a big, deep body of rock. And so that was all going on 80 to 100 million years ago when we had a convergent plate margin. Now, there's a lot of debate in the science and the literature that we had subduction under North America, and then at some other time we had something look more like the island arc off of Japan, off of Asia, the Japanese arc and so forth. And the subduction was going the other way instead of what we call the slab going down to be facing to the east. Then we actually had west-facing subduction. So it was going one way for a while and another way for a while, and the eye of the volcanic arc would crash into the western coast of North America. This is what I mean by it makes for a very, very complex geologic history of California. Okay. More recently, in the low end of the 80 to 100 million years ago, there were changes in the plate boundary. We went from a subduction zone off the west coast to more of a transform or strike slip margin. So this is the San Andreas Fault. Even though I told you, well, it's really not the plate margin. It is. It's in there somewhere. It's a plate margin somewhere between Las Vegas and San Andreas in points offshore. But anyway, this change, when I went from this to this, it wasn't exactly nice and smooth. It's kind of nailed down at one end, which is farther to the north off of Cape Mendocino. Being nailed down and you have plate motions going 3 or 4 different ways, it puts the whole western United States, basically from Salt Lake to here, under a great amount of tension. It's pulling it apart. And that pulling it apart is what has resulted in what we know as a basin and range. If you drive across Nevada, or if you drive up and down, north, if you go east to west, you're going up and down, up and down, up and down. Over mountains, through valleys, over mountains, through valleys. And if you drive from the south to the north, you can get in one of those and just keep on driving and never leave the valley. So that's all because of the plate tectonics and the evolution of how that works. So, and in even more recent times, the uplift of the Sierra Nevada has caused erosion of all the overlying rocks, which were some of these, there were some of the Paleozoic rocks that were above the granite that was in place, it just didn't make it to the surface. So these limestones sitting above it, and uplift raises the crust and it erodes down. And so what happens is we have little bits and pieces of the older rocks sitting on top of the younger stuff. And just for illustration purposes, this is the modern setting. This represents north, so this whole thing is kind of skewed a little bit. But here we are. This is a basin range. Looks like a bunch of caterpillars. And that's the mountains and the valleys. Geologically, we call it Horst and Graben. Somebody will probably come up to you and go, well, is this Horst and Graben? Oh, yeah, sure, of course. And then, here we have the Pacific plate, and here's some other bits and pieces to the north. We're up here. If you go up north, up the coast, once you get deep into Oregon, a little bit, you start noticing active or dormant volcanoes because that is still an active subduction zone. This is the culprit right here. So you have this one go like this, and you have things pulling in different directions. And so what that does is it throws this into what we call extension. When you stretch the crust, it breaks and then it starts, just like corks bobbing on the sea, in a sense. Okay, well, because of the tectonic setting, it's a very seismically active area here. So what this is a map that just depicts earthquakes from 1852 to 2005. The color and the size of the little circles is an indication of how strong or what the magnitude of the earthquake was. So here's Lake Tahoe, and you see, well, a couple of these big red guys they're not too far away, particularly these ones. And these were big ones. These were magnitude 7s. I think that was 1954. And we have a lot of smaller ones, and if you're living in the area or you're living West Reno or whatever, we had quite a bit of seismic activity in the past few years. In fact, there was a couple relatively strong events up here not too long ago, recently. Nothing you can feel it. Okay, so this is something that, you have to worry about at Lake Tahoe. So people say, hey, well, you have earthquakes here? Well, yeah, we do. And it's because we're sitting on the edge of the basin and range province. We have a plate boundary just out here a little bit. And some of that stuff of the San Andreas is actually being bled off, and it actually comes over up through Death Valley and on up into northern Nevada. That's why I say the actual boundary between the plates isn't, you just can't say this is it. It's a broad zone of craziness. Okay, now the geology of Lake Tahoe. Up in the north, we have let's just call them young. Don't worry about tertiary and quaternary. Quaternary is 2 million, tertiary is anything less than about, for our purposes, we're going to say it's less than 20 or 30 million, but it really goes a little deeper. But these are mostly pretty young volcanic rocks. Over on the kind of the southwest and the west, we have, what I say there? Cretaceous and tertiary granitic rocks. So again, these are during the emplacement of that bathymetry. Oops, let's try this one. Same thing pretty much on the eastern shore. I mentioned our isolated Paleozoic metamorphic rocks that were sitting above the granite body, the granodiorite body that was in place during the subduction. They're just kind of sprinkled here and there. And what else we got? And then quaternary, glacial, and lacustrine deposits down here. We have them along the west edge. Not anymore. Yeah. So this is where we're going to. Lacustrine is just a fancy word for lake, related to a lake. So a lacustrine deposit is something, a sediment that was deposited within a body of water, fresh water. Okay, so the north end are volcanic rocks and faults. Here are the big players. These little skinny lines are the fault traces. So here are volcanic rocks. Most of these are 1 to 1.4, maybe a little older. Granites. And I circled the West Tahoe Dollar Point fault that comes on shore just a little east of Tahoe City, and the Incline Village fault. And I think one of my diagrams has the North Tahoe State Line fault in it. So you can see these things they're kind of all over the place. There'll be another slide here in a second. So again, the fault, there are breaks in the Earth's crust along which movement occurs. That's important for everybody. It's important for the seismic geologist. But as a consuming or a public person, anybody, but a private person, you want to know where they are so you don't build your house on one. Or, you know, if your grocery store or shopping center sits on top of one, that you want to be aware of that so that if it ever starts shaking, you know that, yeah, this might be a good idea. Do something, get out of it real quick. It's also important to know what their character is. By character, I mean how often does the fault rupture? Does it break? What's the style of it? Is it the strike-slip thing, or is one side of the fault dropping down relative to the other? What's the potential for ground motion and the displacement? So here we are. I think I got it pretty close. And for those living in incline, you've probably heard all about the incline village fault that runs up into the hills there. It comes in from the lake onto the onshore. All right, so on the west side, it's a very complicated system. All these white lines are mapped traces of faults. Here's this thing right here is the West Tahoe Dollar Point Fault Zone. There's Tahoe City there. Most of these have slip rates in the 0.5 millimeter per year range. It's pretty slow. But these things don't always just slip. They don't always slowly slip. They accumulate it and then they'll pop off. So what's important to understand is how often this has happened and how do we figure that out. We won't go into that. I think you might have another lecture sometime about that. But that's the realm of seismic geology and paleoseismology. Basically, I'm trying to understand seismic events, earthquake events that have happened prehistory. And how do we figure that out? It can be a lot of engineering and building of gigantic civil projects, including the Bay Bridge and nuclear plants and stuff, rely on seismic geology and paleoseismology to provide them with the numbers for ground motion so they can have the proper design criteria. Okay, well, how do we find these crazy things? You know, what we have right here is 3 side-by-side images of the same place. This is just a standard satellite image. You see all the vegetation. This is something more of a radar image, and this is something called LiDAR. I think that's what this one is. Anyway, you can see that the actual resolution picks up in this. I use my hand. This little dark thing here is actually a fault scarp. There is a vertical separation across this planar feature at this point of probably several meters. You can just pick it up in this image, and you can't see it at all on this one. So modern technology has really done a lot for helping us find these things. Here's a LiDAR image of Cascade Lake, Emerald Bay area, and then after somebody went through and analyzed it, sorry you can't see these white on white, but these are traces of faults that they've mapped out through Cascade Lake. And then here's actually a very recent, within the last couple of years, work by Graham Kent and others. This is in Cascade Lake. Their chirp. It's a way for acquiring bathymetric data using seismic reflection. Anyway, the big thing here is they were able to image these plains. These are fault plains, and they also were able to image the sediments that have accumulated. I think water level is probably up here somewhere. They've imaged these sediments, and they've been able to correlate them to other dated sediments to get an idea of when these earthquakes occurred. And I know there are a couple of events about 2,000 and about 5,000 years ago, and then maybe another one about 10,000 years ago. So these things aren't happening every day. they'd take a while before they, I think we might be sick for a while. So that was Cascade Lake, but also within Lake Tahoe, you see him. Here's West Dollar Point Fault. This is USGS seismic reflection data that's really colored up real nicely. They call this eye candy for the geologists like this stuff. And then here's another seismic reflection of the state line fault. You know, the water surface is up here. Well, this is 190 meters beneath their towing vehicle. So that's, you know, this is 600 feet, 1,500. That's 490. Sorry. So this is the bottom. So this tells you for sure. Yeah. When somebody says, "Is it really Lake Tahoe over 1,000 feet deep?" Well, yeah, because here's the evidence for it. We can image the bottom. Well, at where the fault occurs, you see the bottom suddenly jumps up quite a bit. It's about 10 meters. Down at the bottom here, there's something I think the next slide will show, is what was interpreted as the McKinney Bay landslide complex. So we have approximately 25 meters of sediment deposited on top of what has been interpreted as this mega landslide from the west shore. Now, this piston core was only able to go a certain distance down in here to actually try and figure out how old these things are. But it was enough. So, catastrophic natural events. I told you I talked about this in McKinney Bay landslide complex. Hopefully you can see this. You see this big gouge out of the west shore. And then you see all these little things look like shadows and actually look like a little bit of relief. These are actually pieces that came off of the west shore. So big chunks of the mountainside and the shelf along there.
That last slide, where was that on the?
This one?
Yeah, the bottom. Where was that taken on the next slide?
Oh, let's see. This particular thing?
Yeah.
Yeah, this is the state line fault, so it's, I'm not sure exactly where that data was collected, but it's, it's up here somewhere. It's probably, it has to be somewhere where you got the last.
So that was showing that all from that slide, that sediment piled up on top of.
Well, these two, this and this are not in the same place.
The above that green line on the bottom.
Right here, yeah.
All that stuff above that.
Yeah,
is from the slide.
No, this is very fine stuff. This is silt and sand, very very fine grain material. No, the landslide complex is down below it. So it's probably in here. They didn't image it too well. This is back.
So since the landslide, all that silt's built up.
Exactly. So that's one of the things that's if you have this thickness and you know what the rate is that it accumulates, do you think you can do anything with that? It's kind of like how fast you're going. It's a distance divided by speed. How fast can I get there, or whatever. Anyway, you have this 25 meters, and if you know the rate that this is accumulating, then you can just go, oh, it took X thousands of years to accumulate that gigantic, massive, fine sediment. This is a game stratigraphers, geologists play all the time. Well, how can we figure out how old this thing is? We can't date it directly. So, 25 meters in a big lake like Tahoe, that's a lot. So 75 to 100 feet of sediment. That's a lot of stuff. And you go out there today and you can see 100 feet or more down there, and it's like, well, there's not a lot of sediment going in there. There probably never really was a tremendous amount, except for maybe during big glacial periods. So these are all little assumptions you make to try and figure out how old. I'll get to that in a second. So, and here it is. If you take those 15 to 25 meters of fine-grade sediment and apply a rate to that, then you come up with somewhere 60,000, 300,000 years since this thing happened. You know, it's anybody's guess, really. Go back to this one. No, I didn't put that. Well, you can't see it on this one, but elsewhere, there's a more recent reflection across the state line fault. And up in this very upper part, in the upper couple meters, there is what's been interpreted as debris from a more recent earthquake, 2,000, 5,000 years ago. And I haven't done my due diligence to read where those dates came from, but I trust these guys that they collected good information from their cores and then submitted it to a laboratory for dating to come up with those. So they're kind of making a connection between the nature of these deposits. It looks like it came from, or it has a character of a debris flow, and they know when there were some earthquake events, probably from the some of the onshore fault studies they did in the incline fault, the state line fault. So they dig a hole in the ground and start looking at all the sediment, and if they're lucky they find charcoal or something that they can get a radiometric date from. So they start, you know, again, you're playing all these different games to try and narrow it down as to when certain events can happen. It's one of the most difficult parts about being a geologist. So, yeah, so this thing is pretty ancient. I don't know, Heather, have you heard anything recent? One of the guys saying, I mean, they're up here talking all the time.
Yeah, I've just heard, actually heard 30 to 60,000 years ago.
And
later they've increased it again.
Okay, so it just tells you it's really difficult to nail this down.
Yeah.
But it's been a while. But it must have been a pretty good one to shake loose this big of a landslide. I mean, these blocks are huge. They're as big as houses and stuff.
One of them's as big as the Golden Gate Bridge.
Oh, really?
Yeah.
Oh, wow. And they made it all the way to the other side.
Yep.
So the thing I won't talk about, I probably should have, but I'll mention this, that gets people a little worried sometimes if this ever happened again. Shaking would be pretty bad, but then what about the wave, the sage? We call it, it'd be like a tsunami, but they call it a sage when it's in a lake, pretty much. And what would that do here? How would it run up on it? So people have been kind of looking around east shore looking for tsunami-like deposits, and they're there. I know they're there. So as I pointed out earlier, other debris slides recognize the Fallen Leaf Lake and Emerald Bay Cascade Lake, and these things are happening 10 to 15,000 years ago. So again, they're probably related to seismic shaking. It's an obvious hyperleaf. It's not even a hyperleaf. It's a small leaf thing. Okay, I think the last thing we talk about is the glaciations, the ice ages. And in the Tahoe region, there are three main ones that we recognize. Within these are probably all sorts of little stops and starts. The most recent one is called the Tioga. 15 to 25,000 years ago is probably when it was at its maximum. You look up there today and there are a few ice fields here and there. Not many. But you look at the glacial landforms and studies that have been done on these things, and we know that there have been more recent, very minor advances, but these are the major glaciations. So the Tioga, you'll hear people talk about that. The Tahoe, recognized 65,000 and probably another perhaps at 140,000 years ago. Now, this is like, this is deep space for most of us. And then the Donner Lake is a really old one, 400,000 to 600,000. But in the process, they leave behind all sorts of cool stuff for us to look at in the landscape. And it's evidence that helps the geologist piece these different stories together. And as I mentioned earlier, some of these glaciers created changes in the lake level of Lake Tahoe, and we have the deposits that tell us that. So, just to give you an idea how big the Sierra ice cap was during the last, this is several times over the past couple million years. This is about the edge of the southern edge of Mohawk Valley. Anybody's familiar with where that is? Up by Portola, Upper Feather River sort of stuff. Didn't go any farther than that. There's just been some really good studies recently about that. They extended all along the crest of the Sierra. What's interesting is that the actual ice divide during this ice cap was actually farther to the west of the current topographic divide. So Donner Summit was not the ice divide. The ice divide was a little farther to the west. And we know that just because of the information we glean from erosional features from the ice. So we have striations on the bedrock that indicate a westward flow, whilst the erosion, the way bedrock erodes, will be gentle on the upstream side and very steep on the downstream side. And when the ice flows across bedrock, it does a thing called plucking. It basically freezes and grabs a chunk of bedrock and pulls it off, and it leaves this steeper face. So using information like that, we know that the ice was flowing, ice that was east of Donner was actually flowing west. So it's, it's kind of an interesting situation. So, we see somewhere in this area, you see almost all of these different glacial landforms. So here are a couple little cartoons showing the ice and the mountains that are sticking above the ice, and then the landforms that result from these. We have landforms that are related to the debris and the sediment that the glaciers are pushing along, and they usually, when a glacier goes down a valley, it's like a bulldozer, and you have all this debris that's pushing up on the sides. We call those collectively moraines, the ones that are on the sides of the valley. Going down the valley, we call them lateral moraines. And then where a glacier stops, we call it a terminal moraine. Go figure. And then where two valley glaciers come together, then you have two lateral moraines that suddenly join. It's like two highways joining us. It's like the white stripe of two different highways that has to merge. And we're left with these things we call them medial moraines. Here's a beautiful one. This is in the Alps, undoubtedly. More pictures. So when you really have a big ice cap, they're just little pieces, little points of mountains sticking up, and we call those horns. The ridges are arêtes. They're little knife edge ridges and so forth. You walk around here up in the high country, you probably come across some of those. Yes, sir.
Over on this side, east side, the Carson grade glaciers never make it here, or didn't make it here?
Well, interesting that you point that out. So you're going over Kingsbury, right? Yeah. So I come up on Rose Highway, and there's definitely there was glaciation to the east. And I don't know. I don't know about Kingsbury. Wouldn't surprise me, but coming up Mount Rose, it's really obvious.
If you walk up the Film Trail, you see these big boulders sitting around.
Yeah.
Which appear to be, former glaciers. That's one line of evidence, and as a geologist, we try and go on 2 or 3 or more.
lines of evidence. The danger you get in around here is that there's a lot of granite, and it weathers it degrades from the elements: wind, ice, snow, rain. Chemical reactions, the rock starts to break down from the outside in. Granite tends to form these nice spheroidal, rounded features. The best examples are down in Yosemite and Tuolumne Meadows. But they're up here too. You can find them. So you have to be careful, because you can see things that are just sitting out there and they appear to be isolated, but they might be actually weathered in place. So then you start looking for other indications. Now, the big one would be if you're driving down the highway and where those big road cuts, and you see these big boulders sitting in there, and they're kind of floating in this really fine stuff, and then there's smaller gravel and things. That's probably good chance related to glaciers. Now, Mount Rose Highway, there are several places where it's real obvious. And some of those were just very late stage things, little tiny, what we call neoglacial. They were from 600 to 1,000 years ago. A little push, a little cooler climate, snow stuck around enough. There was enough of it, created small glaciers, and it rearranged things a little bit.
So if you go back to that ice cap map, though, the ice cap is really just on the western side. They're not showing a giant ice cap on the eastern side.
Yeah, no, there was no ice cap on the eastern side.
But there may have been smaller, like glacial pockets.
Yeah, exactly. The higher elevations. I mean, you look at Mount Rose, and it has a character to it and a form to it, and you look and you see a snowfield there until the last couple of years. It'd be there until almost July. Now it's gone earlier, but so that when the climate was cooler and there was wetter, that there was probably a lot more snow up there, and perhaps there was enough snow to maintain a small glacier. So yeah, you could have those. It just wouldn't be part of a perennial ice cap.
And then just to be clear for everyone else,
Yeah.
the reason that the east side doesn't have the ice cap on it is because of the rain shadow effect of it coming up over the mountain.
Yeah, exactly. So as the weather, if the weather's coming in from the west, we can't say for 100% that it was always coming in that way, because the circulation models are different for different time periods. But suffice it to say that the moisture was still coming from west to east for the most part. And so the western side is going to be accumulating a lot more precipitation in those times in the form of snow than the east side. So yeah, the rain shadow effect. Thank you for pointing that out. Okay, we're almost done here. So, this is really interesting. How many people live in Truckee? Anybody? You know that one? People come up that, what is it, 89?
Yeah.
Yeah. How many people come up that 89? Yeah. Well, when you do start keeping your eyes out for big, huge boulders along the river, and actually continuing on down the river. A guy that in a sense really wasn't a mentor to me, but I wish he had been, did his PhD work up in Squaw and Bear Creek back in the 60s. And he determined, he didn't determine for sure, but he suspected that the glaciers coming out of Bear Creek will be in Squaw Creek, came all the way across the drainage for the Truckee. So you had ice that came all the way across the valley and blocked off the outlet. So Lake Tahoe is not able to drain. And it raised the shorelines. Now this map, and granted, you can't really see the lines that well, but there's a red one here, and you see these yellow ones, and there's a blue one. These are all different elevations of shorelines. We know that from what a shoreline looks like today, a beach, maybe deposits in them. And way up here, up by the airport, South Shore, there are a couple stream cuts along the upper Truckee where you can see deposits that have to be formed in a lake in standing water. These are annual, they're light and dark bands that are maybe a millimeter or so thick. We call them vars. It's very common in lake environments that go through annual, very cold, very warm cycles. It represents the deposition of organic material. You get different blooms of organisms and so forth in the lake. They're here and they're sitting up at 2,073 meters, and the outlet's at about, I don't know, meters. I can never keep it straight. 6260 feet, something like that. That'd be about 1887, 18 something. Anyway, suffice it to say, this is a lot higher, and these are lake sediments. So how do you do that? Well, that's a nice little model. It actually works. What happens when those things finally break? The dam breaks. Mega flood. So that's why you'll see these gigantic boulders along the Truckee. If you go way down into Reno, before you get to Reno in Verdi, strange pronunciation for, anyway, you get down to Verdi, and by the post office there is a block of granite that's about the size of, it's like a Winnebago. Problem is there's no granite anywhere nearby. Closest granite is like on Donner. So that thing somehow to get itself all the way downstream. So if you do the mathematics, the physics of, or the hydraulics to move water that could move something that big, it's impossible. We used to do that to our students. And, they calculate a velocity of 600-700 feet per second kind of thing. It's like jet speed. And, but they never checked they never thought that, well, that's like impossible to do that. So it had to get there, it had to have some help to get there. And the most logical way to do that, discounting a bunch of other geologic possibilities, is you raft it down on a big flood and it's caught up in ice, which is very, very, very probable. And if you go into some glaciers, Pacific Northwest and so forth, it's not all nice, smooth stuff. It's really nasty. And there are blocks of rock and stuff. They fall off the sides of the mountains. And so here's this giant block that's probably rafted down the Truckee on ice. So it's a nice little model to have these ice dams here. Let's see. So let's look at a little bit more evidence. We're almost done here. It's around Emerald Point, I think. So here's what these black lines represent are old shoreline. We call them shoreline angles. So it's just like the ocean, where the ocean is pounding into the rock cliffs. It creates a little notch. And on the west coast, because there's uplift of the coast and sea level has changed, you get notches at different times. They represent different time periods. The notches here, the shorelines here represent higher lake levels. So we have those. We have moraines that are truncated by shorelines. And then here's a Tahoe age beach road at about 1,902 meters. So that's one bit of evidence. We'll look at one here at Sugar Pine Point and then at Moore Creek. Here we have very fine clay material deposited during a lake cycle. And then sitting on top of that are glacial deposits. So this is out in deep water. This is coming down off the mountains, and the glacier dumps it on top of it. It could be the glacier could have gone out into the lake, which they do, or it could have overrun it later, but chances are this went out into the lake. And then on top of that are beach deposits. So here we have clearly changes in lake level represented in the deposits. And at Ward Creek, this no longer exists. It's been concreted over. But before it was, we got out there and looked at this thing. And so what we have are these things like little slanting sheets of paper. It's really deposit of sand and gravel, they're oriented like this, or sort of tilted. It's a very common form that occurs when a stream is coming into standing water, into a lake. If you ever look at a mud puddle or something, there's water running into the mud puddle, a little stream, you'll see little micro tiny deltas, or even on the streets when it floods. So these are what we call deltaic deposits. So we had Ward Creek coming into Lake Tahoe, and we're I didn't put the elevation up here. We're 20 or 30 meters. Here it is right there, 1908 at the mouth of Ward Creek. And when we say the present lake is around 1890, something like that, meters. So this is we measure it as 20 or 30 feet or meters, I guess, above modern lake. Within that is volcanic ash, tephra, which is possible to date or to look at and correlate to known ashes. So we know that possibly 27,000 years ago there was a lake up at this elevation. And then here's the Tahoe wash, which we know is 15 to 20,000 years ago, 15 to 25. So this works out pretty well. So deep lake, not a deep lake, relatively near shore, but with these deltas deposit, and then a younger glacial advance over top of that. And then here at Baldwin Beach, here's a sequence of progressively older beach ridges at higher elevations from the modern. So finally, this is the 2002 at the outlet, and you can see how low the lake was. It was basically at the sill. And then here's a in-place tree stump. You probably heard about these, read about them. At Baldwin Beach, about 5,300 years was the date on this tree. There are also trees found in growth position in Fallen Leaf Lake, 850 to 1150 AD. So they know the tree died around about 1200 AD. So there was a drought about this time, 850, 1150 AD, and then it came back 1200 AD. So the lake is also recording great ups and downs in lake level, basically telling us climate has changed. So where are we going? So here we go. Same thing I said the first time. This is a take-home message. Sometime 3 to 5 million years ago, what we know is Lake Tahoe probably started forming. But it got its overall start millions of years ago. Volcanism at the north end basically helped block it off, restrict the drainage out of the basin. These faults that are on the sides of the basin allow the central part of the lake basin to be dropping down relative to the mountain blocks. Creates a hydrologic basin as well. We had damming by the glaciers caused lake level to rise well above the modern levels. We saw some of those deposits and landforms that allow us to say this. Large debris slides, McKinney Bay complex, monstrous thing. Not sure exactly when it happened, but tens of thousands of years in the past. Most likely thing is because of seismic shaking, and then we have evidence for severe drought throughout the history of Lake Tahoe. So there you go. I mean, that's kind of in a nutshell. It's not just geology, but unfortunately I have a hard time separating geology from climate and everything else. So there you go. Well, that wasn't quite the 20 to 30 minutes you wanted. But.
No, that was the best one yet, though. That was perfect.
I love it. Every time I come back, she says the same thing. You have tough questions. Yes, sir.
I'm curious, in modern day GPS techniques, it seems to me I've read that it indicates the Sierra Nevada the Carson Range are moving in slightly different directions and stretching the Tahoe Basin. Is that accurate?
I haven't been up on all the geodetics these guys are doing these days, but if you read that in a reputable journal, or even if it was a newspaper article that quoted somebody important, then chances are, I certainly wouldn't disagree with that. I know there was one big project that put a transect at the geodetic stations all the way across the Great Basin, from up around Port Hull all the way to like Salt Lake, and they were trying to get at, what's the relative motion across the Great Basin and where are things moving the fastest. And it turns out that the margins are moving. That's where all the activity is. That's why people get a little nervous around Reno, Carson, Tahoe, because we're close to the mountain front. Mountain fronts are there because there's a reason for them to be going up and the other side's going down. So that's where all the action is. So no, that doesn't surprise me at all.
I think it was Bill Hammond that came in.
Yeah, well, there you go.
He was talking about the Sierras were actually rising,
Yeah.
and they had that evidence since a couple million years of rise.
Yeah,
That's exactly what I was talking about.
Yeah,
Yeah.
and then Graham Kent did the one across the Walker Lane belt.
Yeah.
That it was they have the vectors get quite large as you get right up next to Tahoe.
Technical stuff. The rocks that the Earth's composed of, and all the processes by which they form, as well as overall the history of the Earth. Geomorphology, I will talk about this. It's the study of landforms in the most general sense. It's really the study of the processes that create and modify landforms, and it also encompasses the evolution of the landscape. Plate tectonics is a scientific theory describing large-scale motion of the Earth's lithosphere, the hard outer shell of the Earth. It's comprised of the crust and upper mantle. You've probably heard a lot of these terms just reading magazines and newspapers and so forth. Fault, that'll be a term that comes up time and time again. It is a planar fracture or discontinuity within a large mass of rock. And across that planar discontinuity, there has been relative movement from one side of the planar feature to the other side. Oops. And it's a rapid release of energy when you have movement along this plane that releases a tremendous amount of energy, and that's what causes the ground to shake and earthquakes to occur. Fault zone, just because these things aren't just a simple line that you can sometimes they are, you put your hand on it. Generally, a fault is not just a simple plane, it's a very complex zone of anastomosing planes of discontinuity and so forth, so don't be thrown by the word fault zone. Okay, let's get located where we are physiographically. Here's North America, and we are over here. This is the Great Basin, physiographic province. We're surrounded by the Colorado Plateau to the east, and the Southern Rocky Mountains aren't too far here. A couple other notable points: the Northern Rocky Mountains, the Columbia Snake River Plateaus to the north, and the Pacific Mountain System and the Pacific Coast along the west. Lake Tahoe sits right at the boundary between the Great Basin and the Pacific Mountain System. So it's a unique setting, and just because of where we are within the range and the way the weather systems hit us and so forth, we have up here characteristics similar to the Great Basin, yet somewhat similar to the western part as well. Okay, I have to talk about okay, the introduction's out of the way. I'll try and make this as friendly as possible, but there are a few things that will undoubtedly seem foreign to you, but that's the way it is. So feel free to interrupt me or raise your hand or whatever. All right, I'd like to start out with the conclusion first, and then kind of that sort of gives you an idea of where we're going, and if this thing breaks, then we can all go home. Anyway, the things that you kind of want to, when you're thinking about this, if you're talking to people, the public and so forth, is that Lake Tahoe started forming about 3.5 million years ago. It lies in what we call a structural basin, geologically speaking. I won't really get too much into what that really means, but it's defined by active faults. We'll talk about what faults are. Okay, here are these big words. Pliocene, Quaternary age. This just means the last few million years of Earth history. Volcanism played a role in forming the lake. Throughout its particularly more recent history, during the Pleistocene, which is basically the last couple millions of years, Tahoe was repeatedly dammed by glaciers. It caused the lake levels to rise. There'd be outbursts, and the lake would drain. But anyway, the lake level, we have evidence for lake levels well above the modern level that we see today. We'll talk a little bit about very little bit. When I say we'll talk a little bit about some of this stuff, I really mean it. But we'll look at some of the evidence. Large debris slides have occurred on the west side of the lake, and even much smaller ones to a certain extent on the north side, as well as elsewhere in the basin. They occurred likely in response to seismic shaking, earthquakes.
Question.
Yeah.
How far south did the lava platform extend from volcanic activity?
Probably just, basically the North Shore. There are bits and pieces of volcanics around here, but the main ones were, at this end.
So it's my understanding that the shelf near Tahoe City was called one of the underwater landslides. Was that volcanic in origin?
The landslide or the rocks?
The debris that slid.
I don't really know whether that's volcanic. It would make sense that they're probably volcanic rocks that were involved in the the big slide or whatever, as opposed to what's going on the west shore. Didn't answer your question, did I?
Maybe get to where there's some maps.
Yeah, that'll help a little bit. And then, since we're in the realm of climate change, there is evidence that there have been severe drought throughout the western United States, which impacted the Lake Tahoe region and caused a tremendous decline in lake level well below the natural rim. Okay, so we'll talk a little bit about physiographic setting, the geology and tectonics, the faults and evidence for them, the McKinney Bay landslide complex, the ice ages, Tahoe lake levels, and implications for changing lake levels. So one of the cool things about this particular area is that there is a great diversity in the geology and the geomorphology in the Lake Tahoe region. We have a variety of things in terms of plate tectonic influence, volcanism, glaciers, and using modern techniques to look at things. So it's a great place to be. Before we get too far into this, a couple of definitions. Geology, it's just the science. We talk about the study of the earth, not so much the water, but the solid earth.